An outage at Amazon in December 2021 crippled vast swathes of the internet, impacting everything from Netflix streaming to government websites. A single point of failure in a core service, despite Amazon Web Services' robust design, demonstrated the fragile complexities inherent in distributed systems at the FAANG-Scale. This wasn't merely a bug, it was an architectural challenge echoing across billions of interactions. Distributed systems are not a luxury for companies like Meta, Apple, Amazon, Netflix, and Google, they are an absolute necessity. These architectures break down a monolithic application into multiple independent components, each potentially running on different machines, communicating over a network. This paradigm allows FAANG companies to serve billions of users globally and manage petabytes of data seamlessly. The primary benefit for FAANG entities is unparalleled scalability. When Google needs to process trillions of search queries or Meta handles billions of daily active users, a single server or even a single data center simply cannot cope. Distributed systems enable horizontal scaling, adding more machines to distribute the load and expand capacity on demand. However, this power comes at a significant cost: inherent complexity. Managing state across multiple independent services, ensuring consistent views of data, and coordinating operations across potentially thousands of servers introduces a new class of problems. Debugging becomes a forensic exercise across an intricate web of dependencies. One of the most foundational challenges is network partitions. In any large-scale distributed system, the network will inevitably fail. This leads to the CAP theorem, which states that a distributed data store cannot simultaneously provide consistency, availability, and partition tolerance. FAANG engineers must choose which two properties to prioritize when a network partition occurs. Many FAANG applications, especially those prioritizing user experience and uptime, opt for eventual consistency. Consider Meta's news feed or Amazon's product catalog. Updates propagate through the system asynchronously. A user might not see the very latest update immediately, but the system remains highly available, ensuring continuous service. Conversely, strong consistency ensures all replicas of data are identical at any given time, providing a single, up-to-date view. Google's Spanner, a globally distributed database, achieves strong consistency across continents using atomic clock synchronization, crucial for critical data like financial transactions or user authentication, where data integrity is paramount. The choice between consistency models dictates architectural decisions. Netflix prioritizes availability for streaming content over immediate consistency of watch history across all devices. Apple Pay, however, mandates strong consistency for every transaction, preventing double spending and ensuring financial accuracy. These trade-offs are deliberate and workload-specific. Concurrency control is another critical concept. When multiple services or users attempt to modify the same data simultaneously, conflicts arise. FAANG databases employ sophisticated mechanisms like multi-version concurrency control (MVCC) to allow multiple readers and writers without blocking operations, maintaining performance under extreme load. Data replication is fundamental to fault tolerance and low latency access. Copies of data are stored on multiple servers, often across different geographical regions. If one server or data center fails, other replicas can immediately take over. This is how Amazon ensures your shopping cart persists, or Google Drive files remain accessible. Load balancing is the circulatory system of a FAANG distributed architecture. Devices like application load balancers distribute incoming network traffic across a group of back-end servers. This prevents any single server from becoming a bottleneck, ensuring optimal resource utilization and high responsiveness during peak demand, like during an Apple product launch. Observability and monitoring are non-negotiable for managing systems of this scale. FAANG companies invest heavily in sophisticated logging, tracing, and metrics aggregation systems. Tools like Google's Borman, adopted broadly, allow engineers to understand system behavior, diagnose latency issues, and identify anomalies across thousands of microservices. Distributed transactions, where an operation spans multiple independent services, pose immense challenges. Achieving atomicity, ensuring all parts of a transaction succeed or all fail, without compromising performance is difficult. While two-phase commit exists, its performance overhead means FAANG often prefers eventual consistency combined with compensating transactions for non-critical paths. Idempotency in API design is crucial to prevent unintended side effects from retried operations. For example, if a payment request to Amazon's processing service is sent multiple times due to network retries, an idempotent design ensures the payment is processed only once, preventing duplicate charges. Designing for failure is a core tenet. Techniques like circuit breakers, retries with exponential backoff, and bulkheads are standard in FAANG microservices. Netflix's Hystrix, now a de facto pattern, isolates failures within a service boundary, preventing a cascade effect from bringing down an entire application. Looking ahead to 2026, FAANG distributed systems continue their evolution. Edge computing brings computation closer to the user, enhancing performance for Apple's augmented reality applications. Serverless architectures abstract away infrastructure management, allowing Google Cloud customers to focus purely on code. AI and machine learning are increasingly used for intelligent resource allocation and predictive fault detection. For engineers tackling these environments, the key takeaways are clear: embrace the inherent complexity, understand the critical trade-offs between consistency and availability, design explicitly for failure scenarios, and prioritize robust observability. These principles are vital for building resilient systems. The landscape of FAANG-Scale distributed systems is one of continuous innovation, pushing the boundaries of what's possible in terms of performance, reliability, and user experience for billions worldwide.